John, what are you seeing on your screen at the moment?
That one there.
I'm seeing the D-bus book.
That's it. Okay, we're there. Okay.
Okay.
So that's fine. So normally when we get a speaker here to give a talk on whatever subject, we pick somebody who's got an in-depth knowledge of whatever the subject is that we're going to talk about. Or somebody who's got experience and interest in that particular field. So you're going to get information from the horse's mouth, so to speak. Tonight I'm going to do the absolute opposite of that. I'm going to talk about a subject that I know almost nothing about and have very little practical experience with at all. And it's all going to be based on stuff that's recently been published. And the article that I want to base this talk around tonight appeared in the Dubus magazine, the latest one. Now, for those, how many people take Dubus here? Oh, there's several, about half the room here. Dubus is an amateur radio-based magazine or publication which is of particular interest for people with a VHF microwave background. It's a whole world publication. It's published in Europe and it's published in both English and German in the same magazine. So I can firmly recommend that you get this. It comes out 4 times a year and has the most fascinating stuff in it. So this month Dubus came out, and the subject I wanted to talk about was based on one article. Hang on, sorry. The subject I'm going to talk about is around an article that was published in this about 2-meter ionospheric propagation, something that I knew nothing at all about. And there are a number of other publications such as this that are coming out at the same time. So up in Europe in particular, there's a great interest in this as a weak signal mode capable of very long distance communication on the 2-meter band. Now, ionoscatter as a mode of propagation is not something that's new. We have known about this, but it's been primarily to do with 6-meter propagation. I think I've had one 6-meter ionoscatter contact in my time in Brisbane. When some of the new digital modes were just being introduced, I tried doing some experiments really as a learning process with Rex 7MO and succeeded when there was no other propagation around at all. There was no sporadic E, there was no tropo that would explain how we managed to work from Brisbane to Hobart when there were no signals. So it's been around, it's nothing new in that regard. Now, it's a forward scatter type phenomenon. In other words, the signals go along the path between the 2 stations, and the scattering is occurring in the lower ionosphere at the level of the D layer up at about 85 kilometers. Now, the D layer for radio amateurs is generally considered as the wet blanket that drops over the top of us all during the daylight hours, and this is the reason that you can't hear distant stations on HF during the daytime, because the D layer is reinforced and it just absorbs everything. So it's a giant wet blanket and doesn't do a great deal for HF propagation. And this is the reason you can't hear long-distance medium-wave stations, broadcast stations in the daytime. They only appear at night because the D layer disappears and lets the signals through up to the higher reflecting regions. Because of that height of the D layer, signals that are being bent or that are being scattered from there normally give you a range of about 1,200 to 1,800 kilometers in that zone. Below 1,200 doesn't work because the angle of elevation that you'd need would be too steep. And after 1,800, that's where the signals that are taking off and being received at 0 elevation, in other words, the ground skimming rays, that's the range that you're going to achieve. So it's less than you would get with something like meteor scatter, because that's a phenomena that's occurring higher in the atmosphere up at the level of the E layer. Now, ionoscatter itself is driven by areas of non-consistent electron density in the D layer. So because it's swirling and there are patches where it's more dense than in other areas, that causes interruption of the incoming signals, and that's where the basis of scatter is, where there's a non-discontinuity of density of electrons. So to make use of ionoscatter on 50 megs, where the electron density is low but turbulent, requires very high power and very large antennas. So this is not a weak signal system at all. You've got to have a big, powerful station if you're going to make any use of this. But it's there all the time in patches, and it's the bit of propagation that's still there when everything else has failed. And the principle is that both the stations have to be firing into a common volume in the D layer. So you both got to be aiming at a patch of free electron density, and so the signals, rather in the same way that rain scatter involves using a common volume, you've got to be both aimed at the patch in the D layer where there's some activity. On 50 megs, the signals propagated by ionoscatter are in general extremely weak, and they are awful. It's not quite as distorted as auroral propagation, but not far off. So the signals are subject to very rapid fluttery QSB, and they're unstable in both frequency and amplitude. So they're fluttering and they're being spread. So what's new? Well, what's new in this context, and the basis of the article that Dubas put out, is that there's now an increasing interest in ionoscatter as a mode of propagation on the higher bands, on 2 meters in particular. And not only that, it's become apparent that there are two distinct types of ionoscatter that are going on related to the 2 meter band. And the fact that these are only now being recognized is probably due to a combination of a few factors. One is the increased use of digital communication, which is much more sensitive and capable of finding signals further down in the noise. And as a consequence of that, there's an awful lot of stations who are automatically downloading to a common site all the decodes of the digital signals. So if you're in Poland and you're managing to have a contact in the UK, there might be 20 or 30 other stations in Europe who will decode your signal, and all of those decodes are going onto a central database, so other people can see that these propagation is there and are trying to make use of it. And the third factor, which we'll talk about, is probably global warming. And we'll come to that in a minute. So the first of these two modes of 2 meter ionoscatter, the simple one, is IFS, ionospheric forward scatter. So this is really just the 2 meter equivalent of what we already knew about on 50 megs, but never really had the facilities to make any use of it or to get contacts until the expansion of digital modes for getting through. So this again, as in the 50 meg version, this is a D-layer phenomenon. It requires very high power and big antennas. In fact, the first stations that were recognizing this were EME stations when the moon wasn't up. So they were pointing it at one another, and occasionally we were finding they were having contacts when there was no other mode of propagation apparent. So again, it's related to EMA-capable stations. So these are ones with the high-power, big directional antennas. Because of the geometry, the same as on 6 meters, the normal range of 2 meter ionoscatter is in this same window, the 1,200 to 1,900 kilometer sort of range, but that'll get you across an awful lot of countries in Europe where the amateur population is quite dense. Meteoscatter is further. Normally the maximum range for meteoscatter is about 2,300, and on the low side it's around about 1,000 kilometers. It's tough going below 1,000 kilometers, and to get a contact on meteoscatter out to 2.3 2,300 kilometers, you have to have a meteor that crosses exactly across at 90 degrees to the midpoint of the path. So as you get out towards that limit, it becomes less and less likely, but will still happen. So on 2-meter ionoscatter using ionospheric forward scatter mode, the signals are extremely weak, down in the EME sort of range. They're extremely distorted both in amplitude and frequency. So they're fluttering and they're spread, so they're dancing around in frequency as a reflection of alternating subtraction and addition of multipathing signals from this amorphous number of electrons that they're reflecting off. And in fact, the distortion is so severe that a lot of digital modes won't even decode, particularly FT8 won't work at all. Whisper certainly won't work on this mode, but there are ways around that. Now the second and the more interesting mode of propagation that's occurring in the ionosphere on 2 meters is what's called the mesospheric summer echoes. It's an absolutely awful term. Now mesospheric means related to the mesosphere, and I'll talk to you about what that is, but it's actually one of the layers in our atmosphere, and summer because it's a summertime phenomenon. This is the article that I'm basing the talk on. It's come out of England and goes through. It's a really interesting article. It takes a couple of reads. The picture, incidentally, is of a phenomenon called noxilucent clouds. Noxilucent in Latin means night glowing or night shining clouds. And it's the same physical phenomenon that causes MSE as causes these clouds. And these clouds have been known about for quite some time. They're common to see in Europe. The only bits of Australia where you can see them is down in Antarctica. And the reason that they're of interest to climate scientists is that this is their presence or their expansion is an index of global warming, which I'll touch on in a minute. So just to revise a little bit about our atmosphere. Our atmosphere classically has been divided into these 5 zones. They're concentric. The lowest zone is the troposphere. That's the bit that we live in. Above the troposphere is the stratosphere, and then above that is this mesosphere, the one where this phenomenon is going on. To get some parallel on the right-hand curve there, that curve along where it says ionosphere, that shows the electron density, and so that really shows you where, in comparison, where our ionosphere is, which is what you need to use if you're doing HF communication. So there's a little more graphic display. You notice up in the you can see where the aurora is there, up in the stratosphere there, and where the space shuttle and the International Space Station is. So let's just go through these in a little bit. So let's talk about the troposphere first of all. This is the bit that extends from about ground level up to about 10 kilometers in altitude. This is the bit that we live in. Tropo, incidentally, in Latin just means change. So this is where all the variation goes on. It's where all the weather is. It's where almost all of the water vapor is. It's where aeroplanes fly, and it's where all of the, we normally assume that all our VHF propagation is all tropospheric in one form or another, but not quite. Now, the early climate scientists looking to classify our atmosphere used rockets or balloons to actually measure the changes in temperature and air pressure at different altitudes. And that red line on the right-hand side there, that shows the temperature gradient as you go up in altitude. And you can see that at sea level, the temperature, let's say, is 20 degrees. By the time you've come up through to the top of the troposphere, it's down around about minus 20 or so. You know that as you climb up in altitude, it generally gets colder. Now, it keeps on getting colder up until that line that you see across there called the tropopause. So and this is the boundary between troposphere and stratosphere, called the tropopause, and each of the layers has got an equivalent pause. And at that point, it's been separated out, because at that point the temperature stops falling. And you can see that it in fact starts to go back up again. So in the stratosphere, there's not much up there. It's only a relatively small amount of our atmosphere. The air pressure is extremely low. There's no commercial air traffic up there anymore. Concorde used to fly up there, but nothing else. So there's only a few rockets on the way up, or space shuttles on the way down, or so a couple of spy planes that's up there. But this is the area that also contains the ozone layer, which we all know about. It's the problems of man's influence on the atmosphere. But you can see on that right-hand red curve that as you go up from the tropopause upwards, the temperature starts to increase again. And it continues to increase up to another zone at the stratopause, where it starts to go again the other direction. So the early climate scientists just divided the atmosphere up into the changes that they could see. Inversion layers are down in the troposphere, of course, if they occur. Yeah, I suppose it is. It's certainly a point of inflection where things start to go the other way around. Now, the mesosphere is something I'd never even heard of this. I didn't, meso means middle. So in Latin, this is just the middle layer of the atmosphere. There's not a great deal up there. Atmospheric pressure is extremely low, but temperature starts to climb again, as you can see. Sorry, yes, it does. But I've just highlighted one thing that's up there. This is the point in the atmosphere where noxilucent clouds are found. Extremely high, and they're formed by little collections of ice crystals that are formed around dust that's remaining from the ablation of meteors. So ice crystals form at an extremely high altitude. Because they're so high, the sun sets on them far later in the day than it would set at ground level, and so they're still illuminated by sunlight well into the night period, and that's why they appear to glow at night. Going up further still, we're starting now to go into the thermosphere, and in this area of the atmosphere the temperature starts to go up again. And this is the layer, or the altitude, although it's not contained in, this is the altitude where the ionosphere that we're used to. So the D layer, E layer, and F layer are up in that region, as you can see. And beyond that is really just outer space. So let's talk about mesospheric summer echoes. So in general, this is a phenomenon that only occurs at extreme latitudes, so either north or south 50 degrees or more of the equator. Now, there's an awful lot of land in the northern hemisphere north of 50 degrees. Most of Russia and Iceland, Greenland, parts of Canada, they're all way above 50 degrees north. In the southern hemisphere, not so much. There's a few little bits of all of Antarctica and our bases down there see these noctilucent clouds. The very lowest tip of Tasmania and the lowest end of the South Island, New Zealand, are in this zone. Okay. So we're talking about scatter happening at the level of the mesopause at 85 kilometers, and as we mentioned, the actual physical phenomenon that causes both the noctilucent clouds and this mode of propagation is on meteoric dust, where grains of ice are formed around little bits of dust. And the temperatures are extremely low. This is the lowest temperature in our atmosphere, and it can be as low as minus 150 degrees Celsius. And that
is during summer too.
Yeah. So the high altitude clouds or nano ice crystals occurring in the coldest part of our atmosphere, I don't understand. It does explain, but apparently the temperatures in the mesosphere are lower in the summer period than in the winter. I'm not quite clear, but it's a measured phenomenon. So if you're going to get this effect, it's going to be in the summer months, and that's why the propagation gets this name. So in the northern hemisphere, that's the months of June and July, which is the either side of the equinox, not the equinox, the solstice in the northern hemisphere. But the big difference is that when you get these signals, they are absolutely clear. They're not that weak compared to the forward scatter. The signals have a characteristic of T9 for a CW signal, so CW and SSB are both perfect. A lot of digital modes, even the fussier ones, will work perfectly well, so FT8 will work perfectly well. And you only need modest antennas and power to make use of it. When that propagation mode is running, you don't need a massive EME grade station to be able to work pretty substantial distances. And because it's just that little bit higher, the optimum range is about 1,300 to 1,900 kilometers. So just to reflect again on these noctilucent clouds, that's quite a pretty picture of these clouds. They're also like mesospheric summer echoes. They're caused by these high altitude ice crystals, and they are being used, their presence and their movement is being used as a warning index about global warming from CO2 and other greenhouse gases. And what's apparent is that these clouds are moving further and further towards the equator. Now, why is that happening? Well, the reason is this. When we talk about global warming, the bit that's warming up is the troposphere and the stratosphere, because at that level of the stratopause, which is the limit of it, this is where the CO2 and other greenhouse gases is causing the energy to be reversed back and reflected back towards ground. So the troposphere and the stratosphere, the mean temperatures are rising year on year, but they're doing it at the expense of the next layer up. The mesosphere is actually getting colder because the energy that would normally keep it warm is being reflected back down to ground. So this is why both the noctilucent clouds and this mode of propagation is becoming more and more common, and it's moving back to the more equatorial regions. So in summary then, ionoscatter as a method of propagation is not new. We have known about it. What is of interest, though, is that it's starting to be used and starting to be recognized as a real mode of propagation on 2 meters. It's a forward scattering process. If we talk about the ionospheric forward scatter, the first of the 2 modes of propagation, this occurs at any latitude and it occurs at any time of the year. As we said before, it requires big high-power stations with QRO transmitters and big antennas. The signals that you receive are awful, severe deep QSB and distortion, rough enough to make even SSB unintelligible, and deep enough that you can lose dits and dars out of CW unless it's extremely slow. FT8 performance as a digital method of using this is poor, but the new mode Q65, which is interestingly the mode that we've been adopting up here to do the long-distance microwave stuff, is actually quite effective. It's very forgiving of both Doppler and changes in amplitude. So Rex 7MO down in Hobart has been using Q65 to reflect off auroral clouds with great success, and it's going to work for this mode as well.
Wayne 2X in at Narrabri.
Yep.
And RE 3ZL. Is it that? Yeah.
3ZL, yeah.
They've been, when Q65 first came out and there was talk on this Ionoscatter, they do it quite regularly.
Yep.
On 2 meters.
I've not done it on 2. I've done it on 6 down to Tasmania. I was pretty happy with that. So just to finish up then, just to summarize the mesospheric summer echoes, I wish we had a better term for it. It did at one stage get called auroral D or auroral E, which is totally anomalous term. It's only because it was distorted. So this only occurs on latitudes of above 50 degrees north or south of the equator. So that means it's going to peak also in the summer season in each hemisphere, so that's June and July in the northern hemisphere, but it only requires modest power and antennas. You get near perfect signals, so CW or SSB, and virtually all of the digital modes will work. So I knew nothing about this at all. This idea of taking journal articles and presenting them here will be of interest. I've learned something by reading through it, and I hope that introducing it to the group will be of some value. Thank you.